Hello community, so great that you are back. Today we developed a new core for the next generation of AI. So you remember in my last videos I showed you, currently we are focusing our complete research efforts here in reinforcement learning, multi-agent framework, and we are here at the end of the spectrum, of training a large language model, and we try at the end to correct for reasoning traces and so on. And in my last video, I showed you, even if we go with test time scaling compute, the reasoning model and everything that we have, it has in its reasoning process, it is defined by the base model. It is defined by the pre-training data set. And especially if we look here at the latest QWQ32B that was released yesterday now as the official version and embracing here the power of reinforcement learning and the scaling here in this sector of reinforcement learning, you have here my explanation why those, let's say, scaling of the reinforcement learning paradigm is happening at the end of the spectrum. But you know what? All these beautiful ideas, also from QNet agent and the reward model for a vision language model, everything, and all the effort from Fudan University, Stanford University, Shanghai University, Princeton University, Carnegie Mellon University, Tsinghua University, is great. But everybody tells us, hey, we have a feeling we are at the wrong end of the learning curve here for an AI system, for an LLM, for a multi-agent system. Because we should take here our insight and put it right here at the beginning of the training phase, at the pre-training of an LLM. And today we have a new research by AI Lab from MIT and Harvard University. And you know what? They are exactly now focusing on this idea. So if you want the last 2 weeks, all my videos went from all those beautiful university and all the beautiful PhDs that we had a look at. Now finally is the moment that we say, okay, now we feel that we can do the next step. So looking back here at a week or maybe 2 weeks, let's say all of this was AI version 1.9x, 1.92, 1.93. But now understanding why we have to correct at the end, we are now able to do here the correct learning path for the reasoning right at the beginning. So let's open up this video and let's explore together latest AI research. Now MIT and Harvard tell us, you know what? This pre-training to reason is now our new paradigm for the next generation of AI systems. So we use now reinforcement learning from scratch at the very beginning, and this is now an alternative that we explore to the widely used next token prediction pre-training, the classical pre-training that almost all the systems have. MIT and Harvard tell us using here a curriculum of synthetic tasks, so we start with a very easy task and becomes harder and harder and harder to solve, too easy to learning of a reasoning prior for RL, and I will talk in detail at the end of this video about what is the reasoning prior and why this is the core of our new AI system. And the third point from MIT and Harvard is learning more generalizable reasoning function. This was the topic of my last video. So we need a spark of genius, and I'm so glad that you are back. So let's start. So Howard tells us, hey, designing algorithmic tasks in some esoteric programming languages, never mind, this was just some play new languages to isolate reasoning from memorization. Because in our LLMs, we always have the problem, hey, is the model really reasoning or is it just memorizing some old pre-training data? And MIT tells us here the results showed that state-of-the-art LLMs still struggle to transfer the algorithmic understanding to coding here new programming syntaxes. So it is more a memorization, if you want, a higher degree of memorization, instead of a real reasoning happening, even the latest model that we have. Now, and they go on and say, let's hypothesize that going beyond the current reasoning ability of the current models, it requires a fundamental shift, a fundamental overhaul of the pre-training paradigm. So this is now interesting. They come now from a different perspective. If you want, they come from a different dimension. But we converge exactly with my last 4 videos here on the same topic, on the same point. And they argue, why? Because while a text passage might contain in the classical pre-training data a statement of a mathematical problem and its final answer, it often omits here in the pre-training data the step-by-step derivation leading to the solution. Up until now, we do hear this, if you want, long context reasoning either in the supervised fine-tuning or in the reinforcement learning phase. But what if we would implement this right in the pre-training phase? We would get rid of the problems at the end of the training spectrum. So, they say now we hypothesize that going beyond here this with a new pre-training paradigm, the dominant approach of supervised pre-training here with the next token prediction loss on and what they call passively collected internet data. So I would say string copy internet, followed then by the classical reinforced-based post-training, and all the reasoning models have to rely here on this post-training. They say, you know what? They come from the idea this closely mirrors here a methodology that was implemented by DeepMind in AlphaGo methodology in 2016. And I said, what? It's amazing if you just change the perspective. Absolutely. If you look here at the code or the algorithm of AlphaGo, you see this was from 2016, the latest paradigm. Supervised pre-training with next token prediction loss, followed here by reinforcement learning post-training. But you know what? Just 1 year later, in 2017, this paradigm was overturned by AlphaZero. And here, Google DeepMind demonstrated that reinforcement learning from scratch without supervised pre-training achieved a superior performance. I think it's amazing. We as a community, we stopped in 2016 from the architecture. We did not integrate here the inside of 2017 by AlphaZero, where they did RL from scratch, but we stick to our old architecture, to our old scheme. And now MIT and Harvard tells us, by relying solely here on the self-play and starting from some random initialization, AlphaZero surpassed the AlphaGo, uncovering here a more efficient and more creative strategies through purely reinforcement learning. And this was helpful, but careful. Look closely. I went back to Google DeepMind here, October 2017. This was the original publication here from AlphaGo starting from scratch. And they showed you here about 40 days. And the x-axis, you have 40 days of self-learning algorithms. And you see then day 40, at day 4, passed here the normal player. At day, 16, 17, they passed here the grandmaster. And then it just went beyond human capabilities. But careful, this was the game. This was the complete complexity. It was a two-dimensional sphere with a real limited number, not small, but a limited number of possible combinations. The human natural language, English or German or Spanish or whatever you talk, is so much more complicated, has so many more nuances. So this was an easy environment. So let's come to the core idea, and I already showed you the core idea. If we follow here MIT and Harvard, let's go here with the development of AlphaZero by Google DeepMind. So they now say, hey, looking at this topic from this perspective here, the current AI system, they think that the next token prediction training here on the internet scale data, so string copy internet, may constrain our language models to a local minimum of reasoning abilities. So this means if you think about a hyperplane, then we have here a local minimum somewhere, blob, it's here in the local minimum, and it cannot easily escape and find the global minimum because cannot escape through the post-training reinforcement learning. So this means the reinforcement learning, the post-training reinforcement learning is not strong enough to catapult here our knowledge element out of a local minimum into the global minimum that is the real solution. This is an interesting way to see this. MIT and Harvard go on, it is critical to deliberately disentangle now knowledge from reasoning. We'll talk about this in 2 minutes' time. Allowing the models to develop robust reasoning independent of the memorized patterns. So what they say, hey, the easiest thing to do is now we separate the critical elements. Reasoning and knowledge, memorize patterns. We say, no, they don't belong together. We separate them and we investigate what happens. And they say we propose an architectural modification to our transformer that enables the reasoning system to flexibly adapt to newly added knowledge, ensuring that the model can generalize the reasoning strategy to novel domain. They separate it. So if you think about it, it is rather easy. It is about the quality of the data of the pre-training. Because the classical way here, consider training a model to multiply a number with the data of the form, whatever, where the answers are really directly given. And they ought to say we refer to such data as passive data. That is the outcome of a human knowledge and reasoning. That's the internet data. But it does not encompass here the reasoning process itself. So when the LLM learns on our human data, string copy internet, it does not understand what is the reasoning process behind this, how to derive the result. And they say, so, easy solution, huh? Considering now the alternative of training model on the data that spells out the reasoning algorithm itself, and our latest reasoning models like O1 or O3 or R1 or QWQ32B, they all spell out the reasoning trace, how they come to this conclusion. And they now say we hypothesize that the model has a better chance of learning the underlying algorithm if we clearly see the reasoning traces. So obtaining here a large amount of reasoning trace data is now the challenge that they are facing. And they say, okay, how we do this? And one way to do it is to use, again, reinforcement learning to generate data. So careful. We are not using reinforcement learning in the pre-training only to come up already with a reasoning algorithm. We will do this in a different way. But here we will use reinforcement learning to generate data with a reasoning trace. And how we do this? Maximize the task reward, for example, the correct multiplication or winning AlphaZero, whatever we have as a reward function. I have multiple videos on this. So by structuring now the training here, the pre-training, as an iterative and stepwise problem-solving process, rather than the classical next token prediction on the passive data, our LLM models can now develop more robust and more generalizable reasoning abilities, and we are not limited to some strange pattern observed in the pre-training data, and we are missing the reasoning traces because they are not in the internet data available. So we use now the reinforcement learning in the pre-training in the first step more or less only to generate reasoning traces with some specific reward function that are highly specific. See my last video. They go on in their development of this new core of AI 2.0. They say, okay, as an average human person, the natural language comprises about 40,000 tokens. And doing here reinforcement learning from scratch, you remember our go two-dimensional, and now we have 40,000 tokens here in a free-floating human language space. This is infeasible. So they say, okay, what we do? We are in mathematics, so what we do an iteration. Huh? So we start with a reduced token space. Real simple. Reduced token, nowhere near 40,000 tokens, wherever you have your compute ability. And this reduced tokens, while preserving now the key structural property, here to learn here a reasoning prior. And in this reasoning prior, there are certain functionals, some certain functors. So we have the law of commutativity, associativity, in-context learning, causal reasoning, and more on. So they say we have here a basic set of elements that the reasoning prior has to learn itself, like in this AlphaZero, in a reduced token space. And we are not talking maybe about a language token. Maybe we are just talking an abstract mathematical token. And the token space and the complexity of the token space can gradually then be increased via a task curriculum. So we have a strong, if you want, gradient of more complex topics and the difficulty can increase step by step, and the system will learn step by step. What a beautiful idea. Reduce to the max, have a reduced token space, and in this token space, you learn the basic, 4 or 5 rules of logic. The minimum set, the absolute minimum set. We're not talking about human logic reasoning patterns. We're just talking what is the abstract minimum set of logic. Nice idea. So, in this decoupling of knowledge and reasoning that MIT and Harvard now propose, training models using long context windows, 2 million token, for example, they said, okay, we just found that the longer the context window is, multiple 10 million token, there are some correlation we don't want because sometimes they do not have causal connection anymore between the past and the future token when minimizing here our classical next token prediction loss. So they say, you know what we do? The easiest thing to do, we reduce the set of token in our context window. So instead of 2 million or 10 million context size, we restrict it massively. We build the simplest minimum system that we can think of. And if we have only a very limited set of tokens here, it reduces the chances of exploiting some unwanted correlation between the tokens and thereby promote a more robust reasoning that can transfer the new knowledge domain because we have reduced knowledge domains. We have a reduced reasoning. Maybe we did not even have introduced here the English language, but we are just here in an abstract mathematical structure. So nice. Also here, reduced to the max. And then we have to build the architecture. Yeah? And if we separate now elements that were inherent here in the tensor calculation here in our transformer layers, so what we do, the easiest way is we have an external memory. So if we disentangle knowledge and reasoning into distinct modules, so we have a memory for the knowledge and the reasoning network for the reasoning process. Couldn't be easy, no? And then they say, okay, so for the token context window, we make it really small. And because the reasoning model now operates on a short context windows, it needs here to retrieve and write information to and from the memory. So we do have here an optimized methodology that we have to develop, if you have your CPU and your memory. So this is not such a problem to reduce the context window is not such a problem. And to build an external memory for an LLM, this is standard for any agent. Plus, they come up with a new notation. And this is the most confusing if you read the new study. So let me make it clear. In the classical way, the classical task agnostic pre-training of an LLM using the next token prediction loss function, and we call this a supervised pre-training. Any subsequent training that comes in, continue to optimize this objective for a target task is referred now to supervised fine-tuning, the SFT that you know and that you love. And then we would have a DPO, a reinforcement, alignment here, DPO, and so on. But we are looking at the pre-training formulation and maybe a little bit at the supervised fine-tuning. So we have here the supervised pre-training and the supervised fine-tuning. This is what you know. Now to the new notation. If we now switch over and redefine the core of AI 2.0, we have now a reward-based formulation grounded here in reinforcement learning. So the pre-training done with this reward-based objective is now called the reward-based pre-training. Makes sense, no? Reward-based pre-training, supervised pre-training, great. And any subsequent training to the reward-based pre-training that continues to optimize this reward is now a reward-based fine-tuning, RPT and RFT. Now I understand here, when I read this, I said, what the hell is RFT and RPT? Now we know it. Great. So let's come here to the facts. This is the study. It is beautiful, end of February 2025. And we have it here from AI Lab, from Massachusetts Institute of Technology. And then there's the surprise. From Harvard, we have also the Department of Psychology and the Center of Brain Science. And I said, this is strange. Why not AI, whatever, from Harvard? Why do we have here psychology and brain science? Now, My last two videos, if you have seen them, you will now understand why I've chosen the content of my last two videos. Okay, so they say, hey, since we lack large-scale training data with explicit intermediate reasoning step, and remember the chain of thought topic in my last 4 videos, they say, okay, we don't know how to build this. Yes, and I showed you here a reason from Princeton University with reason flux in one of my last videos, how to solve this particular problem. But now MIT and Harvard go and say they propose here using reinforcement learning to generate such reasoning traces through the interaction with an environment. So this means we are now absolutely purely in robotics, or if you want, if you only focus, we say no vision at all, you want to stay with an LLM. So we have an environment that is, let's say, a human you can talk to and you can learn from. No? And this environment will now provide here some guidance, and we will have to find the appropriate reward function for this. So this is really absolutely important. So they build now the reasoning traces, not like Princeton University here, where we say, let's build some abstract non-linear chain of sorts, where we say we have now some complex reasoning pathways defined in multiple dimensions as an augmentation blueprint. Now we say we want a self-learning system. We want AI 2.0. We have no human data as the starting point. The system should learn everything itself, completely autonomous, self-learning, self-reflective. So we use here reinforcement learning to generate now the reasoning traces, but the system must learn from somewhere. So it must interact with an environment, simplest case robotics, or the system just talks to somebody. And we need the reward functions, because without a reward function, this would not guide the LLM to the correct reasoning traces. And now we understand why Harvard has here the Center for Brain Science. Because, this is kind of similar to the human development. If you think about, you remember when you were a baby? Maybe not. But, this is, Harvard argues, kind of similar to a human. A baby learns here, interacting with the environment and guided by its parents. The baby learns here not on an abstract reasoning level with mathematical logic, but just simply by being in the environment, trying out different things, getting back a reward from the environment. Oh, this is hot, this is cold, this is my bed, this is cozy, this is beautiful, this is wet, this is the bathroom. And the same is happening now in AI 2.0 here, as proposed by MIT and Harvard for the new generation of AI. Absolutely self-learning. Now the critical point here is the quality of the reward function. Now you could guess and say, yeah, like in the baby, you have the parents watching out, taking care, providing feedback, says, hey, careful, don't go over there. This is how you pronounce it, or whatever. This parenting function is now the reward function that we need in our AI 2.0. So this is now kind of a challenge. And yes, you can go with the latest LLM or VLMs. Okay, let's close it up and come to the most important part here. And this is now a level of abstraction I have not seen before. The reasoning prior. You remember? We need a nucleus of intelligence. And this reasoning prior by MIT and Harvard refers now to a minimum set of fundamental reasoning skills that the model needs, the baby LLM needs to acquire before it can really start to reason in a more complex domain, like in natural language, in English, in German, in Spanish, whatever, and interact with its environment. So there has to be this minimal nucleus of reasoning skills. And they go with this: an abstraction possibility, and a hierarchical abstraction, causal reasoning. And you might say, is this the reason why the last 4 videos of you were about causal reasoning? What a coincidence, yeah? Then Howard has this generalization that can be composed in the brain. Understand commutativity, and now you know exactly why I showed you here in a video why the ordering of premises and the rule of commutativity for the premises is so important for the mathematical logic for causal reasoning. This is video 2. And understanding some other rules. And interestingly also an in-context learning ability. This makes it real complex. I exclude this for the moment. But you understand now, talking about this topic. In my last video, I showed you 4 patterns. You remember? Verification, backtracking, error validation, and the correction. And I told you those 4 patterns, if we implement this in a chain of thought, with this minimum patterns, we can build long chain of thought that are now stable. They do not crush, and the answer suddenly goes into loops or just generates hallucination, pure hallucination. With those 4, the stabilization of long chain of context enabled us to build better 3 billion free trainable parameter models. It all comes together now in this video, although they come from a different perspective. Of AlphaGo and AlphaZero, it coincides with my last videos. So let's have a look at this. Learning this reasoning prior here by pre-training the model on syntactic task with reduced token space. Remember, the minimum space. Tasks are carefully designed to incentivize here the development of these fundamental reasoning skills. Maybe this should do a human in the first place. Without the complexity and the noise of a natural language like English, we stay here, abstract mathematical logic. The point is that this syntactic task can teach fundamental logical and mathematical reasoning that are then the building blocks for the real reasoning in English in a human language domain. So by making this token space smaller right at the beginning, also the exploration space for the reinforcement learning becomes much more efficient because the space is smaller. All our search and explore algorithms will be more effective. And then the agent can be rewarded for correctly solving here the syntactic task, and over time, like a little baby, learn to generate reasoning traces that we need for AI 2.0 that reflects here the underlying algorithms. Easy. You know what's the most important? To reflect the underlying algorithm. This is now that we go and we say human thinking, human reasoning. What is our underlying algorithm if human try to apply logic? What is it? Pattern-based? Intuition? So this reasoning prior here is really the nucleus of the next AI generation. They say, okay, train on syntactic task, incentivize the learning of the reasoning primitives with the smaller token space, exploration is much easier, iteratively interact with the environment. This is where we learn from the environment, the feedback, the reward function from the environment. Solve for a specific reward, the agent can develop key reasoning skills. And I just had a look at it, hierarchical abstraction, causal reasoning, yes. Bypassing the complexity of natural language. So the system is not trained on one language like English or German or whatever, but the core of the reasoning is maybe really an abstract mathematical notation in logic. Now the challenge is to come to the niveau where we have this spark that is really happening. This reasoning prior is really operational. And they say, hey, this suggests that we can choose problems in those real small token spaces that preserve the key task properties necessary for the emergence now of this reasoning prior. And one such reasoning prior has been acquired if the spark is there, that it understood the basic logical functions. Then the models can be adapted to a broader token space, maybe 4,000, 6,000, 8,000 tokens, and ultimately to a language, 40 to 100,000 tokens, integrating search and feedback mechanisms into large-scale language pre-training. So a complete new approach to AI. And it made me think. You remember another Austrian fellow, Ludwig Wittgenstein. Die Grenzen meiner Sprache bedeuten die Grenzen meiner Welt. So this means the limit of my language are kind of the limit of my world. There's another alternative that they talk about. What about if knowledge and reasoning is so deeply intertwined, then you just cannot source it off into a memory bank, but it is actually inseparable. So this simplification would lead to errors that we don't want to have. And they say this raises no question about whether knowledge and reasoning can or should even be disentangled in intelligent system. And they say one perspective is that if an agent has to perform a task repeatedly, then this agent may not want to explicitly reason every time for the same task, but it will store the result of its reasoning, one-time reasoning, as knowledge somewhere, and then for the next task simply apply the knowledge and not start a new reasoning process. Is this separable in the architecture? An amazing thought. What do you think about this? And they say, our argument is not that reasoning and knowledge cannot be coupled, but that the agent should have a mechanism to separate them and not only reason based on correlation between its experience so that it can truly apply the reasoning in a more general way. The transferability of a reasoning, of an abstract reasoning pattern to different domain knowledges is our goal. So if we learn something in mathematics, we want to apply in theoretical physics, in I don't know, theoretical biochemistry. Do we achieve this if we separate in the architecture, in the agent, the mechanism for reasoning and knowledge? Is this the way to go, or is there a better way? I think it's a fascinating topic, and it helps suddenly me. I suddenly self-reflect on my own human thinking, how I learn, what I think is my knowledge, what is my reasoning complexity, how can I improve myself, how can I improve my learning? So, real nice, and now is the first time that I can tell you that I see that there might be some parallel development between the human learning and the next generation of AI learning. If you're interested in such topics, hey, why not subscribe? And I see you in my next video.